Okay, guys. Lesson 2.3 is where we're going. Got it? The plan for lesson 2.3 for all that are available to listen, which we're missing like a third of our class between the polls and people being in transit. So, 2.3, polynomial functions of a higher degree and modeling. So, what we are looking at here, some of these higher degrees. We're going to take what we did like last chapter, or last lesson, we did some stuff with linear and quadratics, right? Now we're going to look at the higher degrees, so like the power of 3, power of 4, those type of things. Okay? Now, with that in mind...
Oh, I'm sorry. I tried to go shine over it on my paper.
Oh, can you see okay?
Oh, yeah, I mean, it's not bad.
Okay. Sorry. Okay, I was just trying, because this helped earlier today if I turned off the lights to get rid of the glare. That's what it helps. It helps with my virtual kids. So, okay. So, anyways, what we're looking at here is I'm going to start the notes today. I'll definitely take tomorrow. The way, because it's been a wonky week, it may very easily take into Thursday. Okay. The assignment that's up on the sideboard is also in Skyward, and that is page 193, 2 through 8 evens, 9 through 12 all, and 18 through 28 evens. That is startable tonight, but there's not going to probably be much you can look at. There is a second part of the assignment that I will add on that's 34 through 54 evens. I'm probably going to end up making it all one assignment is what's going to happen. Okay, it's just going to take us a couple of days to get through all of this. Yes, Keaton.
So you said these are like 2 and above, right? Like it's not just like 4 and 5, it's 2 and above, or is it?
Well, mostly I think we work on 3s and 4, powers of 3 and powers of 4, because we've already. Well, I guess I'm thinking about the first part, but I think mostly it's going to be powers of 3 and above, because we've already kind of talked about powers of 2, so we're hitting the powers of 3 and above. Okay. Now. We talked at the beginning of lesson 2.1. We talked some yesterday, 2.2. Polynomial. A polynomial is actually made up of a sum or difference of individual monomials. So we talked about polynomial, how that's adding and subtracting the individual terms. These terms are to be written in standard form. If you recall, you've done stuff with standard form before, where standard form is going, it says descending degree. So we're going from highest power to lowest power. And so the idea of standard form where it's descending degree, so highest power to lowest power, is that the leading coefficient then will always be in front, and your constant term will always be at the end or at the back. Okay, so highest term or highest power to lowest power is your standard form. Okay, excuse me. Now, example 1. My goal is to get through A and B here today. We'll see how we can do. Notice the first thing it says there. Describe. So we're going to use words and describe how to transform the graph of an appropriate monomial function of f of x equals x to the n into the graph of the given function. It does ask us to support our answer graphically. So we will graphically do this by hand, and you can look at the graph on a calculator. And then it also says to compute your y-intercept as a check. Don't let me forget to do that, because I did forget that a little bit this morning. So as you look at example A here, g of x equals 4 times x plus 1 to the third. Thoughts there on what you see in terms of transformations? Left one? The 4 does something. Someone help him out with what the 4 does.
So it's not like over 1 and over 2 over 4. It's like 5.
Okay. What's the words for what that 4 does? It does affect how this graph goes up. When we're multiplying by a number out front, it stretches it. Okay, when you multiply by a number out front, that's a vertical stretch. as long as the number is above 1. 4 is a number above 1, so this is a vertical stretch by a factor of 4. Now, before I write this down, what is the graph that this is being done to? What graph is being moved left 1 and stretched by a factor of 4? Okay, so it's x to the third, right? Okay, so he's talking about the S shape, the cube graph, whatever you want to call it there, but it's the y equals x to the third. So let's go ahead and put that in words, in that we have to, and I'm specifically going to mention, because in this particular problem, we're doing these to y equals x to the third. In another problem, we might use another base graph. So I'm specifically, when I describe my transformations, going to use x to the third there. So we said move 1 left. I'm going to use my official word and say we're going to translate. So translate the graph of y equals x cubed 1 unit left, and the other one was vertical stretch by a factor of 4. I can make that a little bit bigger so you guys can all read it better. Okay, so translate the graph of y equals x cubed, 1 unit to the left, and vertical stretch by a factor of 4. Hello? She already headed to Barb to get her directions from Barb. So she will probably be headed your way soon. Bye. Okay. Are we okay with our describing the transformations?
Yes.
Okay. So next job is we want to graph this. So in this open space here that I left between the beginning of between A and B, we are going to graph this. Hopefully some of you at least left some open space. You'll make it work. Okay. Now, let's see. You need to be able to count 4 up and 4 down for sure. A couple each direction would really work. I'm gonna put tick marks 4 each way, honestly. Okay, so we have a graph that looks like such, or a grid, I should say. We haven't graphed anything yet. Now, the base graph that we're doing this on is y equals x cubed. Now, Ethan kind of alluded a little bit earlier to what it looks like. Can you guys remember what y equals x cubed looks like? Yeah. Okay. I see people draw. I have 2 people have drawn in the air. Hans is flipping back to look. This is in lesson 1.2, correct? Or like 1.3, sorry. This is one of those 12 graphs that I want you to be familiar with. Okay, we have the basic gist of what it looks like. Now, let's talk about a couple specific ordered pairs for it. For instance, if you put in 0 into y equals x cubed, 0 cubed is 0. So it would go through the point 0, 0. This is just before transformation. I'm just getting my basics. What if we plug in 1? 1 to the third is 1. So it's also going to go through the point 1, 1. If we continue and go to 2, what's 2 to the third? 2, 8, which I can't graph 2, 8, which is fine. If we go 1 the other way, what about negative 1? Negative 1 raised to the third is negative 1, so left 1, down 1. Now, it kind of looks like a straight line, but you guys know it's not a straight line, right? It's that cubic graph. And so I'm just drawing this in pencil so that you have, that's just my pencil. That's what a basic y equals x cubed looks like, right? Old news, I hope. Now, we have to transform that. So what do we have to do to this graph? We have to take it and move it left 1 and stretch it by a vertical factor of 4. Now, if we move this left 1, what happens to this center 0, 0? Yeah, at negative 1, 0. Now, and each of those points would move left 1, correct? Think about a vertical stretch by a factor of 4, though. Do you remember talking about this? What does a vertical stretch do? What does it affect?
The high of the graph.
Okay, how high the graph is, which means are we affecting the x's or the y's? The y's, okay? So my x's aren't going to change. It's the y's. This y was at 0, 0. Now we moved it over to negative 1, 0. The y value either way is 0. What's 0 times 4? 0. So that it's not a vertex, but that center point is still going to be at 0, negative 1. It's not going to change because it's on the x-axis. A vertical stretch does not affect it. Now, think about the point 1, 1. It was right 1, up 1. You move it left, it's left to right 0 and up 1, yes? So what's the y value? Y value is 1. When you stretch it by 4, 1 times 4 is 4. And so where does this end up at? 0, 4. So we have a point at negative 1, 0. We have a point at 0, 4. And let's do the same thing with the other point. It was at negative 1, negative 1. You move it over, it's going to be at negative 2, negative 1. But the y value is negative 1. You multiply that y by that negative 1 by 4, it becomes negative 4. So now I end up with negative 2, negative 4. And those new points are what you can draw there, or what you can connect. You can definitely tell the moving left 1. Can you tell how the vertical stretch looks? My graph looks taller now, doesn't it? Or more stretched out, so to speak. Okay. Questions on how that one worked? Sorry, I have an eyelash or something in my eye that's bugging me here. Okay, let's try B. See if we can get B done before we run out of time. Okay. What are your thoughts on B?
It's right to up 5 and reversed.
Right 2, up 5. What do you mean reversed?
Like it's like instead of like
Flipped? Dang it. Okay, backtrack. A, we were supposed to compute our y-intercept as a check. Maggie, I said remind me if I forget. Yeah. Well, totally spaced it. Okay, so real quick.
Yeah, I just saw it and I was like, wait.
We didn't do that. I did the same thing second hour. So, okay, y-intercept. A y-intercept is where your graph crosses the y-axis, right? What do you know about the x value then? Y-intercepts happen whenever x is 0. So let's see what this is when x is 0. Let's find g of 0 real quick. G of 0 means 4 times 0 plus 1 to the third. Well, 0 plus 1 is 1. 1 to the third is 1 times 4 is 4. So right there, I just got a y-intercept of 4. Does that match with what happened on my graph?
yeah.
It does. So are we good? We are. Y-intercept is the easiest point ever to check because it's always when x equals 0. Okay, thank you. I'll get it right one of these days. Maybe not soon enough, but okay. B. You guys were telling me, right 2, up 5. I was looking for the official words that Keaton was trying to come up with. Reflects across the x-axis, right? And I think that's what Keaton had in his brain. It just wasn't coming out in those words. So it's, it's good. So reflects across the x-axis is at negative. And what graph is this being done to? Y equals x to the 4th. Okay. So I'm going to write it all out. We're going to have to reflect the graph of y equals x to the 4th across the x-axis and translate right 2 and up 5 units. Okay. So I wrote, reflect the graph of y equals x to the 4th across the x-axis and translate right 2 and up 5. You left room for your graph this time? That's good. So I am going to draw a set of x and y axes again, and then we can talk about what this graph is going to look like. You have to allow yourself room to go at least up 5. A couple to the right, a couple to the left, that type of thing. But you have to be able to go up 5. I think I pretty much count 4 on the others. Not that you have to, but. Okay.
I don't know how this stuff looks like.
Okay, so he's stealing my question there. I saw Hansa turn and look to that page of 12 graphs. Do we know y equals x to the 4th? Is that one we've talked about? It's not. So, you get off the hook on this one. I'm not going to be mad if you don't remember what y equals x to the 4th looks like. But we have these lovely calculators, right? Did anyone try it on the calculator? Let me try and get myself out of the glare here. Okay, y equals, this is just basic y equals x to the 4th. Looks like kind of what? A parabola, except that it's flatter at the bottom and goes up steeper. For reference sake, real quick, what's drawing on top of it, that red, is y equals x squared. So do you see the differences there? A parabola kind of is less flat, it goes out more. The y equals x to the 4th goes up straighter and has a flatter base. Okay? So that's what a basic quartic graph does. There are other versions of it, but that's the basic for right now. Now, if you think about this, let's get some basic dots in here real quick. If we just think about x to the 4th, if you put in 0, 0 to the 4th is 0. If you put in 1, 1 to the 4th is 1. So it goes through 1, 1. If you put in 2, 2 to the 4th is 16. I'm not graphing 2, 16. If you put in negative 1, negative 1 raised to the 4th is positive 1. So here in pencil, I'm just showing you the basic graph here. Okay, there's your basic quartic graph. Now, what do we have to do to this? It's just like moving a parabola, isn't it? Flip it upside down, and then move that vertex where? Right 2, up 5. So I'm going to go right 2, up 5. There's my new vertex. What did the first dots do on the other one? They went over 1, up 1. So since I'm upside down now, I can go over 1, down 1. Over 1, down 1. And so your quartic is what it's called. Looks something like such. Not exactly the best, but we'll go with it. Now, what am I supposed to check?
The Y thing.
The y-intercept. So let's put in 0, because this is a good one to look at. The negative of 0 minus 2 raised to the 4th plus 5. 0 minus 2, negative 2. Negative 2 to the 4th, positive 16. The negative of that is going to be, or the opposite of that is negative 16 plus 5. Negative 16 plus 5 is negative 11. Does that check? Well, we don't really have a y-intercept graph, do we? Does it make sense that I could have a y-intercept of negative 11?
Yes.
It's going down, it's headed that way. So to me, that's a check. Even though we don't have it, now if my y-intercept was positive 11 and my graph is upside down, headed the wrong way, that's the problem. Does that make sense? Okay. Homework. Page 193, you can get started on it, but you don't have to worry about anything being due tomorrow. I'd say the soonest anything's going to be due is Thursday. Okay? And I don't know. I'll see you guys all one way or another somehow tomorrow. Not sure how. I don't know. Maybe I'm losing hope. Maybe we'll be here.
No, I think you're just realistic.
I mean, is that what it is? I'm being realistic here?
I think so. I stopped being positive after all the things that happened. I'm not negative.